In this lecture, we will learn how to install and configure a clustered environment on Linux. A clustered environment means using two or more computer servers that work together as a single system. These servers are connected so that if one server fails, the other one automatically takes over its work. This setup is mainly used to provide high availability, which means services keep running without downtime. We need this because in many businesses and applications, stopping a website, database, or service even for a few minutes can cause big losses. For example, if an online shopping website like Amazon runs on one server, if that server crashes, the whole site goes offline. But if the site runs in a clustered environment with two servers, when one fails, the other continues serving customers without interruption. Clusters are also useful for sharing workload between servers so performance improves and systems respond faster. In simple words, clustering ensures reliability, availability, and better performance for important services. Let's move on and create our clustered environment, where we will connect two CentOS machines and test the process of failover from a Windows machine. Failover means that if one server in the cluster stops working, another server automatically takes over its job without stopping the service. Here, the CentOS servers will act as the cluster nodes, sharing responsibility for running the services. We will also use a floating IP, which is a single IP address that can move between the two servers. So clients always connect to the same address even if the server behind it changes. Here, the Windows machine will not be part of the cluster, but will be used as a client to test connectivity, such as pinging the floating IP or opening a web page to confirm that failover is working properly. Let's get started.
Hi, I am Imran Afzal. I make learning technology easy, even for beginners in IT. So I have over 25 years of experience in Linux administration, Windows, virtualization, and many more. I have taught millions of students worldwide.
Here we have two CentOS machines running and connected through PuTTY. On the left side, we are working with the first machine, which has the host name, my first Linux VM, and the IP address 192.168.100.215. On the right side, we are connected to the second machine, which has the host name, my first Linux OS, and the IP address 192.168.100.229. Along with these two Linux servers, we also have a third machine, which is a Windows system. The host name of this Windows machine is Imran, and its IP address is 192.168.100.154. This Windows machine is not part of the cluster, but it will be used as a client to test our setup. Let's move on to the My First Linux VM machine and make it full screen so that the commands and output are easier to see clearly. This will help us focus step by step while setting up the cluster. The second machine, My First Linux OS, will not be shown right now, but we will switch to it when needed during the configuration process. The first thing we do is to run the command dnf repo list all to check all repositories available on CentOS and see which ones are enabled or disabled. This is important because cluster packages such as Pacemaker and Corosync are found in the high availability repository. Here you can see that the high availability repo is present but currently disabled, so we need to enable it before installing our cluster software. Let's move on and enable this. For this, we open the repository file using a text editor such as Vim. This file is found in the directory /etc/yum.repos.d/ and the file name is CentOS stream high availability.repos. We need this file because it contains the configuration details of the high availability repository, including whether it is enabled or disabled. When we go inside this file for the first time, it may look empty because sometimes the repo definitions are not fully written or are commented out. In such cases, we have to manually add or adjust the entries and set enabled is equals to 1 so that the system knows where to fetch the cluster packages from. Here we have already created a Word document where we are writing all commands and steps, and we will also upload this document with the lecture. This makes it easy for learners to follow along without typing everything themselves. Here you can see the repository settings, which we copy and paste into the file so that the system knows how to configure the high availability repository. This setting starts with high availability, which is the name of the repository. The name field gives a human readable description. Here it is a CentOS stream, high availability. The base URL tells the system the online location where the packages are stored and from where they should be downloaded. The line enabled is equals to 1, means the repository is turned on so it can be used. The GPG check is equals to 1 ensures that the packages are verified with a GPG key for security before installation. Finally, the GPG key field shows the location of the key file that is used to verify these packages. Let's save and quit this file after making the changes. Now we need to refresh our repository settings so the system can load the new configuration. Let's run the command to clean all old cache, which removes previously stored metadata files. After that, we run the command dnf make cache to create a new cache, which means the system is refreshing its list of available packages. It goes online, connects to the repositories, and downloads the latest information. Here you can see in the output that the high availability repository is now listed together with base, OS, AppStream, and extras. This shows that the high availability repo is enabled and ready, so we can now install the cluster packages from it. Now all is set for the installation of our cluster software. So it's time to install the required packages, which are Pacemaker, Corosync, PCS, Resource Agents, and Fence Agents all. Pacemaker is the brain of the cluster. It is the main service that decides which server will run which resource. And it makes sure that if one server goes down, the other server will immediately take over without downtime. Corosync is used for communication between nodes. It keeps both servers in touch with each other, shares heartbeat signals, and ensures that every node knows the current status of the cluster. PCS is the management tool that we use to configure the cluster easily with commands. Instead of editing complicated files, it helps us set up nodes, resources, and properties. Resource agents are like ready-made scripts for different services such as IP addresses, web servers, or databases, so Pacemaker knows how to start, stop, and monitor them in a standardized way. Fence agents are used for fencing in real setups, which means if a node becomes unresponsive or misbehaves, it will be forcefully powered off or isolated to protect the shared data and ensure no corruption happens. Together, these five components work hand in hand to build a reliable, high availability cluster where services remain online even during failures. Here you can also see the option -y is used with the install command. This simply means that the system will automatically answer yes to any confirmation prompts during installation. The -y flag is flexible. You can write it at the start or at the end of the install command, and it will work the same way. Let's wait until the installation is complete. Now you can see that the installation has been completed successfully without any errors. Let's move on and start the PCSD service, which is the PCS daemon responsible for handling cluster configuration and communication. We enable it, which allows the service to start automatically on every boot, and at the same time, we start it immediately. After that, we check its status to make sure it is running correctly. Here you can see in the output that the PCSD.service is now active and running, which means the PCS web interface and remote configuration system are working. Now let's switch to the second server machine, which is my first Linux OS. On this node, we will repeat the same process that we already did on the first machine. To keep things simple and save time, we will fast forward through these steps because they are exactly the same as before. So it's important here that both servers must have the same setup so they can work together properly in the cluster. Now all the process is completed on the second machine as well. We have enabled the repository, installed the cluster packages, and started the PCSD service. You can also see the status here, which shows that the PCSD service is active and enabled, meaning it is running properly and will also start automatically on every reboot. This confirms that both servers are now ready and fully prepared to move forward with the next steps of configuring the cluster. Now let's move to the first machine. And here we configure the firewall so that cluster traffic can pass between the nodes. We add the high availability service to the firewall permanently, then reload the firewall to apply the change. After that, we check the list of allowed services, and we can see that high availability is now enabled successfully. We repeat the same process on the second machine as well. As you can see from the output, the result is also successful there, which means both machines are now ready to communicate with each other for the cluster setup. Now it's time to configure the cluster authentication user. For this, we first use the command to set a password for the special user called HA cluster, which is created by default during the installation of PCS. Here we write the password and confirm it. The system shows a warning saying bad password. The password is shorter than 8 characters. This happens because we use a small or simple password just for testing purposes. But in a real environment, you must always set a strong password that is at least 8 characters long and contains a good mix of letters, numbers, and symbols for better security. Even though the system shows this warning, it still accepts the password for now and updates the authentication token successfully. We do the same thing on the second machine and set the password for the HA cluster user. There as well, we make sure to use the same password on both machines so that they can trust each other and communicate without issues. After that, we go to the first machine, and here we write the command to authenticate both nodes with the HA cluster user. When we run it, you can see it does not work and it shows errors saying it cannot communicate with the machines. Why is this happening? The reason is that the host names are not resolving because we did not add them correctly in the slash etc/host file. So before running this command, we must make sure that the slash etc/host file contains the correct IP addresses with host names of both machines. So we edit the slash etc/hosts file, and at the end of this file, we add the entries for our two servers. These entries make sure that when we use the host names, my first Linux VM or my first Linux OS, the system knows their correct IP addresses. After adding these lines, we save and exit the file. We repeat the same step on the second machine as well so that both nodes can resolve each other's names correctly. This step is very important because without it, the cluster nodes cannot communicate properly. Now we write the same command again to authenticate the nodes. Here we can explain that using the IP addresses of the servers is often more reliable because IPs do not depend on host name resolution. But you can also use the names of the servers if they are correctly added /etc host file. That is why here we use the server names, my first Linux VM and my first Linux OS. When we run the command this time, you can see that both nodes are successfully authorized, which means the authentication is now complete and the two machines are ready to be joined into the cluster. After that, we run the command to set up the cluster by giving it the IP addresses of both machines. After running this command, you can see that it first clears any old cluster configuration if it exists, then it generates the authentication keys, and finally distributes those keys and the configuration file to both servers. The output shows that files like Corosync auth key, Pacemaker auth key, and corosync.conf are successfully sent to both nodes. At the end, it clearly says cluster has been successfully set up, which means our two servers are now joined together and the cluster is ready for the next steps. Now we start the cluster services on our nodes. Because after setting up the cluster configuration, the services like Corosync and Pacemaker must be restarted so they can load the new settings and begin proper communication between the servers. Here you can see in the output that the cluster starts running and the time is also shown when the services are activated. We do the same thing on the second machine as well, and you can see that both machines are now online and part of the cluster, ready to manage resources together. Then we enable and start Chronodeep, which is the service that keeps our system time correct using NTP. This is a very important step in a cluster because both servers must always have the same time. If the clock are different, the cluster can get confused. One node may think the other is offline when it is not, or events may be recorded in the wrong order, which can even cause data problems. After enabling Chronodeep, we run the time date CTL command to check the status. Here you can see the local time, the universal time, and the time zone. Since we are in New York, the time zone is shown as America, New York. The output also confirms that the system clock is synchronized and the NTP service is active, which means the time is accurate. We do the same thing on the second machine, and here you can see that both machines now show matching times, which confirms that synchronization is working correctly across our cluster. Then we go back to the first machine, and from here we can start the cluster services on both machines at the same time because the PCs tool allows us to control all the nodes in the cluster remotely. When we run the command with the option minus minus all, it doesn't just start the services locally, it sends the start signal to every node that is part of the cluster configuration. That's why even though we type the command only on the first machine, you can see in the output that it connected to 192.168.100.215 and 192.168.100.229 and started the cluster on both. The message starting cluster confirms that the cluster services are running successfully on both servers without us needing to log into each machine separately. After that, we also run the command to enable the cluster so that it will automatically start every time the machines reboot. In the output, you can see that both nodes show cluster enabled, which confirms that our cluster is now active, enabled, and will always stay running even after a restart. After that, we changed two settings to make the cluster work better in our test. The first setting is stoneth enabled is equals to false. Stoneth is a feature that shuts down a bad node to keep data safe, but we don't have that set up here, so we turn it off. The second setting is no quorum policy is equals to ignore. Normally, if one server goes down, the other server stops working because it thinks is not safe. Since we only have two servers, we tell the cluster to ignore this rule so the other server can keep working. Then we create a cluster resource, which is like the shared service that both machines will manage. In this case, the resource is a floating IP address. A floating IP is an IP that doesn't belong to just one machine. It can move between the two servers in the cluster. We set this floating IP to 192.168.100.220 with a net mask of 24, which means it works in the same local network as our servers. We also add a monitor option with an interval of 30 seconds so the cluster keeps checking if the resource is healthy and running properly. This way, if one machine goes down, the floating IP will automatically move to the other machine, and clients can still connect without any problem. After that, we check the cluster resource to confirm where the floating IP is running. You can see in the output that the resource named cluster IP has started on the server with IP 192.168.100.215, which is our first server. This means the virtual IP address 192.168.100.220 is currently active on this machine. If this machine goes down, the cluster will automatically move the IP to the second server. This is how high availability ensures our service stays online without interruption. Now we move to the Windows machine to test if our cluster IP is really working. For this, we use the ping command and enter the floating IP address 192.168.100.220. You can see in the output that we are getting replies back with 0% packet loss, which means the IP is live and reachable. This shows that the cluster successfully assigned the floating IP and it is available on the network. So our high availability setup is now verified from the client side as well. Now it is time to test the failover process, which is the most important part of a high availability cluster. To test this, we stop the cluster service on the first machine with IP address 192.168.100.215. As soon as we stop it, you can see in the output that both Pacemaker and Corosync on this machine are shut down. After stopping, we go back to our Windows machine and run a ping command to the floating IP 192.168.100.220. Even though the first server is stopped, the ping still replies without any packet loss. This shows that the floating IP has automatically failed over to the second machine, meaning the cluster is still available. Next, when we return to the first server and run the command PCEC status, the system shows an error saying connection refused and asks if Pacemaker is running. This error is normal because Pacemaker was stopped on this server, so it cannot show cluster information. The cluster itself, however, continues running smoothly on the second server, which confirms that the failover mechanism is working correctly. By confirming this test, We now go to the second server and check the cluster status using the PCS status command. Here you can clearly see that the cluster is still running fine even though the first server with IP 192.168.100.215 is offline. In the node list, it shows one node as online with IP 192.168.100.229 and the other as offline with IP 192.168.100.215. Under the full list of resources, the cluster IP resource is shown as started on 192.168.100.229, which means the floating IP has automatically shifted to the second server. In the daemon status, all cluster services, Corosync, Pacemaker, and PCSD are active and enabled. This confirms that the failover has worked successfully and the cluster is still available through the second server without any downtime. So this is the real advantage of having a clustered environment. Even if one machine goes down, the service is still available from the other machine. See you in the next lecture.
If you enjoyed the lesson, please give it a like and share your thoughts in the comments. My team and I have worked so hard to make learning simple for you. Thanks for watching, and let's keep learning together.